Hi, in this video we are going to talk about insertion sort, so let's get started. It is a very efficient algorithm, and one of the main advantages of insertion sort that it's very easy to implement. And as we have talked earlier, for example, as far as Fibonacci heaps and binary heaps are concerned, usually Fibonacci heap doesn't worth the effort because it's very hard to implement it efficiently, and that is true for all the other algorithms. We usually prefer algorithms that are very easy to understand and very easy to implement, and this is the case with insertion sort 2. It is efficient for small data sets, and that's why merge sort and quicksort relies heavily on this algorithm. We are going to talk about both merge sort and quicksort, and we will see that on small subarrays, this insertion sort can outperform merge sort and quicksort, and so merge sort and quicksort usually uses insertion sort as a sub-algorithm. It is efficient for datasets that are already substantially sorted. It is stable, so it doesn't change the relative order of elements with equal keys. It is in place, which means that only requires a constant amount of additional memory space. And it is an online algorithm, it's very important, can sort a list of it, receives its data. For example, if we are downloading integers from the internet, it's not so realistic scenario, but if this is the case, then we can sort it with the help of insertion sort. So insertion sort requires lots of writes because the inner loop can require shifting large sections of the sorted portion of the array. In general, insertion sort will write to array quadratic times, where writing to memory is significantly more expensive than reading, such as with flash memory. We should use other sorting algorithms, and this is the main disadvantage of insertion sort, that there are lots of shifts, as we are going to see during the illustration. So let me show you an example how it works in practice. We have an array of integers 7, 4, 6, -2 and 1, and we want to sort this array. So we start at the leftmost element, and we keep comparing it with the previous elements, and because in this situation this is the first, there are no previous elements, we keep hopping to the next one, which is 4, but 4 has a previous node, previous neighbors, so we keep comparing 4 with its previous nodes, in this case 7, and we came to the conclusion that 7 is greater than 4, so we swap the two of them. We hop to the next one, which is 6, and we keep comparing it with all its neighbors, leftmost neighbors, so 7 and 4. So we came to the conclusion that 6 is less than 7, so we swap the positions, and we keep comparing. 6 is greater than 4, so we just do this. Keep hopping to the next item with -2. -2 is less than 7, it is less than 6, it is less than 4. So as you can see in this situation, there's a lots of shifting. We keep incrementing the number of items we want to be sorted and do lots of shifts. Okay, and the last item is 1. We just compare it with 7, 6, 4, and we come to the conclusion that we compare it with -2, but -2 is less than 1, so this will be the case. This will be the solution to this problem. So that's all about insertion sort. Thanks for watching.